Good morning. Myself, Mr. Dibyendu Mondal, Assistant Professor of Greater Kolkata College of Engineering and Management under GIS Group. This is the class of solid mechanics. Today we are going to discuss about principal stress. This is my lecture number 10 of module 1 and this is the completion lecture of first module. If you have any query, you may ask anytime through phone or over mail. Okay, let's start. Principal stresses and strain. First one, the concept of definition of stress, strain, types of stresses, tensile, compressive or simple shear, types of strain, tensile, compressive or shear, and volumetric strain are discussed. The stresses were acting in a plane which was at right angles to the line of action of the force. Actually, principal plane and principal stress, the plane, actually principal plane and principal stress means the plane which have no shear stress, okay, which has no shear stress are known as principal planes. Here, hence the principal planes are the planes of zero shear stress. These planes carry only normal stresses. The normal stresses acting on a principal plane is known as principal stresses. Method for determining the stress on oblique section. There are two types of method. One is the analytical method, another one is the graphical method. Analytical method for determining stresses on oblique section. First one, the following two cases will be considered. A member is subjected to direct stress in one plane. P, that is the axial force acting on the member, and A, that is the area of cross section which is perpendicular to the line of action of the force P. The stress along x sigma is equal to P by A. Hence, the member is subjected to stress along x-axis. Consider cross-section EF which is perpendicular to the line of action of the force P. Now, the two diagram. Here, the P is the tensile and EF, that is the perpendicular, and FG, that is the inclined at an angle theta. So P is the stress, and sigma, one is the 90 degree minus theta, another one is the 90 degree, this angle. P PTOP, that is the 90 degree minus theta. So here area of section EF, that is equal to EF multiplied by 1, that is equal to capital A. The stress on the section EF is given by sigma is equal to P by A, force by area of cross section, A, capital A, P by A. The stress on section EF is entirely the normal stress. There is no shear stress or tangential stress on section EF. Now, consider a section FG at an angle theta with the normal cross section EF as shown in figure. Area of section FG, that is equal to FG into 1. Actually, member is having unit thickness EF by cos theta into 1. So that is equal to A by cos theta. Stress on the section FG, that is equal to force by area of cross section P divided by A by cos theta. So P by A cos theta. So that is equal to sigma cos theta. The stresses on section FG is parallel to the axis of the member. That is, the stress is along x-axis. The stress may be resolved in two components. One component will be the normal to the x-axis. This stress is along x-axis. This stress may be resolved into two components. One component will be normal to the section FG, whereas the second component will be along the section FG. So one is the Pn. Pn is the component of the force P normal to section FG. That is equal to P cos theta. Actually, horizontal one is the horizontal P cos theta, another one component should be P sin theta. Sigma n is equal to normal stress across the section FG. Sigma t, tangential stress across the section FG. Okay, tangential stress, that is shear stress across the section FG. Normal and tangential stress, normal stress and tangential stress across the section FG are obtained as sigma n is equal to force normal to section FG, that is the area of section FG. So here Pn divided by A by cos theta is equal to P cos theta divided by A by cos theta. So here P by A cos theta into cos theta. So P by A cos square theta. So that is the sigma cos square theta. Tangential stress sigma t, tangential stress or shear stress sigma t, tangential force across section FG, area of section FG. So Pt divided by A by cos theta, P sin theta divided by A by cos theta. P by A sin theta into cos theta. So sigma sin theta into cos theta. So that is equal to sigma by 2 into 2 sin theta cos theta. That is equal to sigma by 2 sin 2 theta. Actually 2 sin theta cos theta, that is equal to sin 2 theta. So from equation 3.2 it is seen that the normal stress sigma n on the section FB will be maximum when cos square theta or cos theta is maximum, and cos theta will be maximum when theta is equal to 0 degree, as cos 0 degree equal to 1. But when theta is equal to 0 degree, the section FG will coincide with section EF, but the section EF is normal to the line of action of the loading. This means the plane normal to the axis of loading will carry the maximum normal stress. Maximum normal stress equal to sigma cos square theta, that is equal to sigma cos square 0 degree, that is equal to sigma. Across the section FG will be maximum when sin 2 theta is maximum, and sin 2 theta will be maximum when sin 2 theta is equal to 1 or 2 theta is equal to 90 degree or 270 degree. And 2 theta is equal to 90 degree, so theta is equal to 45 degree. Okay. This means that the shear stress will be maximum. Shear stress will be maximum on two planes inclined at 45 degree and 135 degree to the normal section EF. Maximum value of shear stress sigma by 2 sin 2 theta, that is equal to sigma by 2 sin 90 degree. So that is equal to sigma by 2. Okay. Now here the first plane of maximum shear stress theta is equal to 45 degree. Here from equation 3.4 and 3.5 it is seen that maximum normal stress is equal to sigma whereas the maximum shear stress is equal sigma by 2 or equal to half the value of greatest normal stress. Second method, a member subjected to a direct stress in one plane. Okay, actually a rectangular member of uniform cross-sectional area capital A of unit thickness, the bar is subjected to a principal tensile stress sigma 1 on the faces AD and BC. So this is the cross-sectional area. Area of cross-section is equal to BC into thickness of the bar. Let the stresses on the oblique plane FC are to be calculated. The plane FC is inclined at an angle theta with the normal cross-section EF or BC. This can be done by converting the stress sigma 1 acting on faces BC into equivalent forces. Tensile stress on BC is the tensile stress on BC that is equal to only sigma 1. Force is equal to sigma 1 multiplied by area. Area is equal to BC into 1. The above tensile force P1 is also acting on an inclined section FC in the axial direction as shown in figure. This force P1 is resolved into two components, that is one normal to the plane FC and other along the plane FC. Okay, so Pn is equal to component of the force P1 normal to section FC P1 cos theta, that is equal to sigma 1 into BC into 1 into cos theta. Another one is the component of force P1 along the section FC P1 sin theta, sigma 1 into BC into 1 into sin theta. Normal stress on the section FC shear stress or tangential stress across the section FC, then the normal stress sigma n is equal to force normal to section FC divided by area of section FC. So that is equal to Pn divided by FC into 1. Sigma 1 into BC into cos theta divided by FC. So sigma 1 into cos theta, so sigma 1 cos square theta. Similarly, tangential shear stress, actually follow the diagram. So tangential stress sigma t, that is equal to force along section FC divided by area of section FC. So PT divided by FC into 1. Sigma 1 into BC into 1 into sin theta divided by FC. Sigma 1 into cos theta into sin theta. So sigma 1 by 2 sin 2 theta. It is seen that the normal stress sigma n on section FC will be maximum when cos square theta or cos theta is maximum, and cos theta will be maximum when theta is equal to 0 degree, as cos 0 degree is equal to 1. When theta is equal to 0 degree, the section FC will coincide with section EF, but the section EF is normal to the line of action of the loading. Okay, this means the plane normal to the axis of loading will carry the maximum normal stress. Maximum normal stress is equal to sigma 1 cos square theta, that is equal to sigma 1 cos square 0 degree is equal to sigma 1. From equation 3.5 it is observed that the tangential stress across the section FC will be maximum when sin 2 theta is maximum, and sin 2 theta will be maximum when sin 2 theta is equal to 1 or 2 theta is equal to 90 degree. This means the shear stresses will be maximum on two planes inclined at 45 degree and 135 degree. The normal section EF and BC is shown here. Now, it is very important, maximum value of shear stress sigma 1 by 2 sine 2 theta. So that is equal to sigma 1 by 2 sine 90 degree. Okay, so maximum value is equal to sigma 1 by 2. From equation this, maximum normal stress is equal to sigma 1, whereas the maximum shear stress is equal to sigma 1 by 2 or equal to half the value of the greatest normal stresses. A rectangular bar of cross-sectional area 10,000 mm square is subjected to an axial load of 20 kN. Determine the normal load, normal and shear stresses on a section which is inclined at an angle of 30 degree with normal cross-section of the bar. Cross-sectional area of the rectangular bar A is equal to 10,000 mm square. P is equal to 20 kN. Angle of oblique plane with the normal cross section of the bar theta is equal to 30 degree. Sigma is equal to P by A, 20,000 divided by 10,000, 2 Newton per millimeter square. Sigma n is equal to normal stress on an oblique plane. Sigma t, shear stress on the oblique plane. So normal stress sigma n is equal to sigma cos square theta, 2 into cos square 30 degree, 2 into 0.866 square, 1.5 Newton per millimeter square. Shear stress we get sigma t is equal to sigma by 2 sin 2 theta, 2 by 2 into sin 2 into 30 degree. So that is equal to sin 60 degree, that is equal to 0.866 Newton per millimeter square. Find the diameter of a circular bar which is subjected to an axial pull of 160 kN if the maximum allowable shear stress on any way, any section is 65 Newton per millimeter square. Actually, given axial pull is equal to P is equal to 160 kN. So that is equal to 160,000 Newton. Maximum shear stress is equal to 65 Newton per millimeter square. Capital D is equal to diameter of the bar. Capital A is equal to area of the bar, pi by 4 into d square. Direct stress sigma is equal to P by A. So 160,000 divided by pi by 4 into d square. 640,000 pi d square Newton per millimeter square. So maximum stress is given by, actually maximum stress, the value of maximum stress we know sigma by 2, this one, but maximum shear stress is given as 65 Newton per millimeter square. Hence, equating these two values, the maximum shear, we get 65 is equal to 64 into 000 divided by 2 pi d square. Now, d square is equal to, after calculation, d square is equal to 640,000 divided by 2 pi into 65 is equal to 1567. A rectangular bar of cross section area, cross-sectional area 11000 millimeter square is subjected to a tensile load P as shown in figure. The permissible normal and shear stresses on an oblique plane BC as given 7 Newton per millimeter square, 3.5 Newton per millimeter square respectively. Determine the shape value of P. Area of cross section A is equal to 11000 millimeter square. Normal stress sigma n is equal to 7 Newton per millimeter square. Shear stress sigma t 3.5 Newton per millimeter square. Angle of oblique plane that is the 60 degree. So angle of oblique plane BC with the normal cross section of the bar theta is equal to 90 degree minus 60 degree, that is equal to 30 degree. P is equal to safe value of axial pull. Sigma is equal to safe stress in the member. Sigma n is equal to sigma cos square theta. 7 is equal to sigma cos square 30 degree. Sigma is equal to 7 divided by 0.866 into 0.866, 9.334 Newton per millimeter square. Using this equation, sigma t is equal to sigma by 2 sin 2 theta. So 3.5 is equal to sigma by 2 sin 2 into 30 degree. Just substitute the value of 60 degree. So sigma is equal to 3.5 into 2 divided by 0.866, 8.0338 Newton per millimeter square. Safe stress is at least of the two 8 point this, and safe value of axial load is equal to safe stress multiplied by area of cross section. Okay, safe stress, তাহলে safe value 8.083 into 11000, that is equal to 88.913 kilonewton. So after calculation, safe value of the axial pull, that is equal to 88.913 kilonewton. Okay, safe value of axial load. Now, so this is the actually today we discuss the principal stress. Thank you. This is the end of my lecture. If you like my lecture, you have to subscribe my channel, and if feel free, you may contact any time to clear your doubt, okay, through mail or through WhatsApp or through mobile phone. Okay, thank you.